Okay. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Ramadan Mubarak and good afternoon to all of you. Inshallah, today's meeting is going to be about simulation of power electronic systems for photovoltaic applications, introduced by Dr. Abdelali El Aroudi, Department of Electronics, School of Engineering, Rovira University in Virgili, Spain. Welcome, Doctor, and thanks for joining us today. Yakallah.
Thank you very much for this kind introduction.
Thank you.
Assalamu alaikum, everyone. Ramadan Kareem. So my name is Abdelali El Aroudi, and in this lecture, I will give you this talk titled Simulation of Power Electronic Systems for Photovoltaic Applications. I'm from the Department of Electronics, Electrical Engineering, and Automatic Control of University of Virgili in Tarragona, Spain. I have to acknowledge the support of the International Scientific Partnerships Program, ISPP, at King Saud University. Thanks to Professor Mohammed Al-Numay for making this collaboration possible. This is the outline of my lecture of today. First of all, I will start by introducing you to PV systems. Then I will present the basic structure of a PV system and why power converters are needed in this kind of systems. A short introduction to power converters. Then I will be talking about the types of PV-based electricity generation systems, the control task design in this kind of PV system, some theoretical background, and I will start simulation of a complete PV system, but first by simulating the different ingredients that this system involves. So start in this part of simulation, I will start by describing the system to be simulated. Then I will simulate the different ingredients of this PV system. And finally, I will simulate the complete PV system, which has a power rating of about 10 kilowatts. So the outcome or the learning objective of this lecture are the following. First, to know PV systems, to understand the operation of basic power converters topologies, to know Pcm software for simulating power electronics converters, to learn how to simulate the different ingredients of a grid-connected PV system using this software and similars, and to learn how an Mppt control algorithm in a PV system operate, and finally to strengthen the simulation skills of power converter circuits for PV applications. The lecture consists first an introductory part to PV systems, and then a second part dealing with to show how to perform numerical simulations of power electronics converters in PV applications using Pcm software. But first, the theoretical aspects are briefly introduced, and the simulation of the different ingredients of PV system are performed, and finally, the simulation of a complete PV system will be carried out. So let us start talking about PV systems. What is a PV system? A PV system is each system that is composed by PV generators and power electronics converters and load. Maybe this is the first application of a PV system that has been appeared in the space, not in the earth, where PV generators are mainly used for powering satellite. In the earth, there are different kinds of PV installations. There are what we call large-scale PV generation systems, and the tendency now is toward small-scale PV generation systems. So in many countries, they are starting to use PV system in homes and different residential parts of the city. This is a very nice application of a PV photovoltaic generation systems, where we can see that This is a street lighting application where we have the PV panels powering the batteries during the day, charging the batteries, and during the night the battery are used to power or switch on the loads, which are LED, light emitting diodes. This is a small PV system in the desert where it is necessary to cool water, for example, or to keep medicines in a desired temperature. This is a small PV system in a telecom system where we need to power the antennas used in the telecommunication systems. So this is the part of the PV array of the roof of our research group in Tarragona, in University Rivera in Virginia. We have this total 60 modules and 5 kilowatt as a total power generated from this PV installation. Another PV installation that we have in the campus is this PV arrays in the library building, and it is used for lighting the library during the day. So the main important aspect of a PV system is the PV generator. The problem of this PV generator is that, I'm sorry, I will activate the, The main problem of the PV generators are their nonlinearity. They are not a current source, neither a voltage source, but they have a nonlinear characteristic in the voltage current characteristic. And it is very important that the PV system operate at the maximum power point, which is indicated here. So for example, if the voltage and the current drawn from the PV is this one, the power will be this one, corresponding power will be this one, which is very far from the maximum power. And as I mentioned before, it is very important that our system operates always at this maximum power point. If we connect the load directly to the PV source, depending on the value of the load, we might have the system operating in the maximum power point, which is this case, for example. But there are also other value of the load, resistance in this case, that will make the system to operate far away from the maximum power. So it is necessary to put between the PV source and the load a power converters that will make the load seen from the source equivalent to the one corresponding to the maximum power. So we need power electronics. What is power electronics? Power electronics is a field of electrical engineering that deals with the application of power semiconductor devices for the control and conversion of electrical power. So basically we have power converters with the specific source, and we have a load, and at the output of the converter, we have an output that we must control. So we have to put the controller with the specific reference, and the controller sends the desired output of the load of the power converter, and the controller acts in such a way that this output match exactly the reference signal. The heart of a power electronic system is a power converter. So what is a power converter? Here, before speaking about power converters, this is an application where power converters are used. For example, as I mentioned before, interfacing PV sources and the load, with the main objective of making the PV source to provide the maximum power to this load. So basically, the power converter, what it will do is to adapt the load seen from the PV source. So that it matches the one corresponding to extracting the maximum power. And this process is called the maximum power point tracking. So what is a converter? A power electronic converter is a circuit made of energy storage elements and semiconductor devices, operating as switches that use different switching state to change the magnitude and the waveform of the voltage at the input, providing another voltage at the output with a different magnitude. It can be considered as a DC equivalent of an AC transformer. We know that the transformers usually are dealing with AC signals. So a power converter is like a transformer, but it is a DC to DC transformer.
Mm-hmm.
The main important thing in power converters is ideal efficiencies. This means that the power at the input side is equal to the power at the output side. And if the power at the input side is equal to the power at the output side, we have the equality, the voltage at the input multiplied by the current at the input will be equal to the voltage at the output multiplied by the current at the output. For controlling switch converters, we use square wave signals with the specific time duration and period, and the ratio between the time duration where the switch is activated over the total period is called duty cycle. And you can see that duty cycle is always between 0 and 1. These are some basic converter topology widely used in the literature. We have the back converter, the step down converter, which convert an input voltage to a lower output voltage. We have the boost converter, and according to this formula, we can see that it step up the voltage. I mean, if the duty cycle is between 0 and 1, this formula demonstrates that the output voltage will be always bigger than the input voltage in this boost converter. And finally, we have the back boost converter, whose expression for the output voltage is given in the slide. And this can be used either for stepping down or stepping up the voltage at the input. This is an example for a PV application. So we have a PV panel, we have a DC-DC boost converter, which is detailed here. And the objective is to drive this switch in such a way to extract the maximum power from this PV source. And in order to do that, we have to select the right duty cycle that give the maximum power of the PV source. So this is a PWM, pulse width modulator, which generate the pulses on and off to drive this switch. And by switching this device, we convert the voltage at the PV from a low value to another voltage higher than the input by specifying the right duty cycle to convert, to extract the maximum power from the PV source. All these things will be simulated later, and I hope it will be much clearer later. So this is another kind of power electronics converters topology. This is an inverter, the basic inverter topology, which is called the H-bridge inverter, and it is its operation is very similar to DC-DC converters. The only thing different is that it converts a DC input to an AC output. So we have at the input maybe PV generator or maybe a DC bus, and the output of the inverter, in this case, it is a single phase inverter. It is an AC signal, sinusoidal AC signal. So as I told before, the tendency in the present is to move from high power converter using in large scale PV generation systems to small PV generation systems based on low power converters, like for example, those used in residential applications. The picture at the top of the slide shows a large scale where you can see the inverter is a huge building of power electronics system, while in the low side of the bottom side of the slide, the inverter can be very small and it's deal with very small amount of power. In the large scale PV generation systems, they use or usually use single stage configuration, while in small scale PV systems, the approach used is the two-stage, where we have a DC-DC converters to perform maximum power point tracking and a DC-AC inverter to perform power factor correction. This means that its operation is such a way that it injects to the grid a sinusoidal current, which is synchronized to the grid voltage. This is power factor correction. So this is basically the system that we simulate in this lecture. It is basically a two-stage approach, which is currently the most common PV installation used. And basically we will start by simulating the PV source, by simulating also the Mppt controller or the Mppt algorithm. We will simulate the DC-DC converter, which is the boost converter with this Mppt algorithm. We'll simulate the inverter, and finally, we'll simulate the complete system. So as I told before, the DC-DC converter is responsible for setting the PV operating point to be the maximum power point. And evidently, because it is a boost converter, it steps up the PV voltage to a higher DC voltage. So the DC voltage here between the inverter and the converter must be higher than the voltage at the output of the PV source. And the inverter is responsible for performing power factor correction. It means that it will inject sinusoidal current into the grid, and this current will be synchronized with the grid voltage in order to perform this power factor correction. The control variable for the DC-DC inverter is the RMS current reference, or equivalently also its amplitude. Please note that we have a PV source, which is a DC input, but we have an AC grid. So we have DC to AC conversion, and we have to put here an energy storage to deal with this mismatch between DC and AC. What I mean is that here we have constant power generated from the PV, but here we are injecting through the DC-AC inverter, we are injecting AC power. This mismatch or this difference must be balanced by using an energy storage, which is in this case a capacitor. So a capacitor here is needed to deal with the difference between the PV power and the AC power injected to the grid. And it can be demonstrated by a very elementary calculus that the power handled by this energy storage element is given by the power produced by the PV generator multiplied by the cosine of the double of the grid frequencies. So we will expect that at the capacitor, we will have an oscillation which is twice the grid, oscillation with the frequency equal twice the grid frequency. So as I said, the capacitor provides energy storage necessary to balance the differences between the DC power and the AC power. So this oscillation will make that the PV power could be either bigger than the AC power or less than the AC power. When the PV power is less, when the DC PV power is less than the AC power, the capacitor is discharged. And when the PV power, the DC PV power is larger than the AC power, the capacitor will be charged. So we will have this periodic charge and discharge of this capacitor, and evidently we will expect that the voltage at this DC link will have an oscillating behavior with a frequency equal to twice the grid frequency. So the case study that we will consider is illustrated in this slide. We will use 12 models, each one of the double of 450 watt. And it gives, this power is given at full radiance. It means 1000 watt per meter square. If the PV arrays operate at the maximum power, we will have this power, which is calculated by multiplying the power of an individual module by the number of rows and the number of columns. So we have 12, so 3 by 4, 12. And the total power will be generated by this PV generator is 10.8 kilowatts. The total surface that this PV installation will occupy is about 26 meters square. We will use an AC grid voltage of about 230 volt. And for this amount of power, the RMS value of the grid current to be injected to the grid must be about 46 amperes. So this information is taken from a commercial PV model, which is this one. The power rating is between 440 and 465 at full irradiance. The efficiency of the PV model is about 21 according to the manufacturer. And the manufacturer also gives this information, gives the height and the weight of the PV model. It gives also the maximum power voltage, which is about 41 volt for each model. The maximum power current, which is about 10.98 amperes. And it gives also other important information as illustrated in this table. So in order to simulate this PV installation, we'll use Pcm software. This is my favorite simulating power electronics software for simulating power electronics circuit. This software has now 25 years as age, and its stable version is very recent. It is version 2021A, and it is a version of January of this year. It operates in Microsoft Windows, and there are different license types. And there is also a free demo version, but it has some limitations. So it can be used for simulating power electronic system, but also for many other applications, like for example, for general circuit, digital and logic circuit, for also control, for practicing control theory about analog and digital, for electric machines, and evidently as it is designed for power electronic system, it also can simulate photovoltaics and wind turbine sources. Pcm is widely used by both industry and academia. And it has an easy to use user interface. You will see that it has graphical circuit diagram, and also it's present the result in a very simplified way. Basically, it has two different programs. The first one for drawing the circuit, and the second one is for illustrating the simulation results. So now we will start making some simulation. I think it's time to start already. So we will run simulation of PV generator, only the PV generator for different value of irradiance, and observe the PV power and the PV voltage curve. Okay, so in order to do that, I will switch to Pcm, and I hope you can see my screen again.
Yes, we can.
Perfect. Okay, this is the main window of Pcm. This is the complete system that we'll simulate. But now I will disable Pcm. Pcm has this ability to disable any part of the circuit, and I will apply only the PV generator. Okay, I will leave only the PV generator, and I will apply to this PV generator a voltage source. And I will calculate the drawn current from the PV source and the drawn power. The power is calculated just by multiplying the voltage of the PV source by the current drawn from the same PV source. So I have here the power, and I have here the current. The current is sensed by this current sensor, okay? So if I apply a voltage varying from 0 to its short circuit voltage, I will be able to generate the PV curve. Let's try. I hope I don't have any mistake, because when I disable something, it is always probable that I make some mistakes. But I think now it is.
Hopefully it will work, inshallah, Doctor.
It will work. Let's see. It is simulating.
Okay.
Okay. Here we can see the simulation bar. It is
Loading.
arriving to 100%. Okay, now it is uploading the data. Now it is uploading data. When data is available, I will draw. Okay, this is not what I want to show you, so I will remove this. Okay, I will draw the current first. Okay, now I will see. Just a moment. I think I have made a mistake. Is it?
Not a problem at all, Doctor. Not a problem.
Yeah, well.
Take your time.
Okay, just a moment. I will see what is the frequency of this signal. It is 100. So yeah, this one must be very small. I will simulate again. It will be much faster, in fact. Yes. Okay, this is what I wanted to show you. And I don't know if you are familiar with the PV panels curves, but this is the voltage, current, or I will change the x-axis to voltage.
Instead
I
of
can do it in Pcm. Okay, so you can see this voltage current characteristic of the PV panel. And as I told at the beginning, it is a nonlinear curve. And if I draw the power, you see that this is the power, and I will draw it also as a function of the PV voltage. And you can see that effectively we have a point where the power is maximum. And in this specific power, this specific PV generator is the one that we will use in our simulation. Remember that I told you that we will use a PV generator that totally generate 10.8 kilowatt. So you can see this is the maximum power generated, and you can see it is 10.8 kilowatt. Okay, so this is the first simulation that we have performed only the PV generator. So we can do that for different irradiance. For example, we can.
But Doctor, just to make sure, we have to use the x-axis to perform the voltage. Is that correct?
Yes. Normally, yes. Good question. Normally, the Pcm give you the result automatically as a function of time. Okay, but Pcm also has this functionality of changing x-axis and converting it to any variable you have in the system, any current, any voltage. So I take advantage of that, and I changed the time, which is the x-axis, with the PV voltage. Okay, this is your question. I think it is.
Thank you very much. That's clear.
Okay. As I told before, we can do this for different value of a parameter. For example, we can do that for different value of irradiance. If we put here, for example, Pcm doesn't allow to change the irradiance directly, but I will use a track. So I will use this one, but I will multiply this one by a parameter, and this parameter can be changed. I will call it S, okay? And this parameter can be changed by using parameter sweep. Parameter sweep exists in Pcm. I will show you how to do that. So I think we have elements, other parameter sweep, okay? In the parameter sweep, we have to specify which parameter we have to change or to sweep. We call it S. the start value. For example, I will change it between 500 or between 200 and 1000. And we will make increment of 200 in order to have, for example, like 5 or 6 PV curves. So we will make simulation again. Okay, now we have different, let's make again this one. I will put this, okay. We will make all the current generated, this one, this one, this one, this one, and all of them plotted as a function of, again, I will change the x-axis. I will put it voltage, because they are the same voltage, anyone can be used. Mm-hmm. They are, sorry, this is not what I wanted to do. If I leave it time, it is better. Okay, I will leave it in time. So you can see that we have different curves for different irradiance, and we can do the same also for the power. So the power, we have this one, this one, this one, this one, and finally this one. And we can see also that we have different levels of power. We can zoom here, and you can see.
Yes.
You can see as the irradiance is changed or varied from lower value to upper value, the maximum power available in the circuit increases. So evidently, this is the curve corresponding to 200 watt per meter square, and this is the brown curve correspond to the maximum irradiance level. Okay, so this is how to generate PV curves in Pcm. So let us now move to the slide to see what I have to present again. So these are the curves that we have obtained. So I have shown you how to obtain them with Pcm, even with parameter sweep. This is the current voltage curve, and this is the power voltage curve, and it corresponds to the PV generator that will be used in our PV system. So one of the task of a PV system is maximum power point. As you could see before, that the PV curve changed as the irradiance changed, and we are interested to track the maximum power for the different value of irradiance. So for that, we use maximum power point tracking. This maximum power point tracking automatically adjusts the desired PV voltage so that to extract the maximum power from the PV source. How to do that? So it can be done by using this flow chart. We have to initialize our parameters. In our case, we'll use the duty cycle of the converter as the duty cycle or any other parameter as a control variable. We have to store this value, and we have to store also the odd value of the power. And we have to measure the actual value of the power and make a comparison. If the actual value of the power is bigger than the old value of the power, we have to increase the parameter. And in the other case, in the contrary, we have to decrease the parameter. And this process is continued till arriving to the maximum power. Okay, this is an illustration of how a maximum power point tracking algorithm works. Basically, if we are at the left of the maximum power, we have to be able to detect that and move to the right. And if we are at the right, we have to be able to detect that we are at the right and move to the left. This is the algorithm. And it is use always steps or changes in the direction of increasing the PV power. And this is called hill climbing. So in my case, I have implemented this algorithm by using this simple C code, okay? Pcm allows to use a block, and this block can be programmed using C language. So I use this code, which implement exactly this flowchart. And first we will apply it to a PV source without any converter, just to see how this MPPT works, okay? So instead of connecting a DC-DC converter, we'll connect only a controlled voltage source. And this Mppt algorithm will automatically, by means of this controlled voltage source, will automatically make the PV voltage to match or to be equal to the maximum power voltage. So let us do that with Pcm again. Okay, we will make this circuit. I think I have it already implemented. So we will, maybe this one, yeah. So exactly what I said. Now I don't need that. This was for generating PV curves. I am using here the controlled voltage source, and the C code is in this block. The C code, as I told before, is inside this Mppt block. And let's do some simulations. Okay, here I have the PV extracted from the power from the PV generator. You can see that it is in steady state now. It is exactly the power that we mentioned before. In fact, I can also plot the maximum power available. It is this blue curve, and you can see that in steady state, the power of the PV is exactly the power, the maximum power available in this PV generator. We can also plot the PV voltage, and you will see that the PV voltage is in steady state, oscillating at the voltage corresponding to the maximum power. Okay, this is how Mppt algorithm operate. Okay, so we have here very important parameters to know how the effect on the behavior, on the speed of the Mppt controller. We have the period of the Mppt. You can see here that the Mppt variables are oscillating. So we have a period of perturbation, and we have also an amplitude of perturbation. These two parameters are very important to know because they have a huge effect on the speed of the algorithm. So let's try to change, for example, in this simulation, we will change. Let's start with, for example, making this amplitude bigger. Let's put, or by starting, for example, by making the period of the Mppt larger. If I make it larger, it will be very slow. So I will make it smaller. Instead of 2 milliseconds, I will use 1 millisecond. So let us simulate again, and you will see that it will converge faster. Did you see that it converged faster?
Yes, but if you can, Doctor,
yes.
Repeat it again, please.
Yes. Now I am playing with the period of the Mppt. Okay. First, I have 2 milliseconds as a period of the perturbation in the Mppt algorithm, and we had this behavior. We can see that the PV converges to the maximum. The PV power converges to the maximum power available, but it takes, like, let's say in this case, 0.9 seconds to arrive the maximum power. If we make this period smaller, we can see that the settling time or the reaching time is smaller. Okay? Let's move again to 2 milliseconds. And now, instead of changing the period, we will change the amplitude of the perturbation. Instead of using 1 millivolt, we will use 5 millivolt as a perturbation. And you can see, you will see the result. Now it is simulating. And you can see it is also faster than the beginning, even faster than before. But you can see that the oscillation amplitude is larger. So this will make the power efficiency smaller, because if the amplitude is larger, the oscillation amplitude of the power is also larger, and we are losing a little bit of power. Okay, so this is how Mppt algorithm operates. Okay, by adapting the voltage of the PV panel so that it matches the maximum power voltage, and for that we have to play with two different parameters. In this case, we have the period of the oscillation of the Mppt and the amplitude of the perturbation. Okay, this is what we did, and we have obtained that. I have already simulated that. We have seen that this behavior would, I don't know if I have used the same parameters or not, but the idea I have already illustrated it.
It's clear, yes.
Okay, so let's move to use, instead of using a voltage source, now we will use a boost converter. Okay, we will forget now about the DC-AC inverter. We'll deal with it later. But now, instead of using a PV generator with a voltage source, we will use a PV generator with a DC-DC boost converter. Okay, so we will control it in this way. We will use PWM, pulse width modulation, where the duty cycle will be given by the Mppt controller. But let's start by giving directly the duty cycle. We know what is the value of the duty cycle to give the maximum power, in this case for full irradiance level. And we will use this value. Then we will make this duty cycle to be provided by the Mppt controller, just to understand the importance of putting the right value of the duty cycle in order to extract the maximum power. Okay, so we'll use this circuit for simulation. And if the DC bus here at the output of the boost converter is 380, this is the value that we use, which is a standard value of PV systems. And we know that the PV voltage is 248. A simple calculations led us to know that the duty cycle at the maximum power point is equal to 0.3474. So let us use this value as a duty cycle. So we will use Pcm simulation, and we will obtain some result. Okay, let's move again to the other circuit. Now we will activate, or we'll activate the DC-DC converter. I hope you can recognize this converter, and we will use directly, let's see what I can do here. I have to remove this, I have to remove this. This is disabled, and I'm given the right duty cycle value, 0.3474, in order to extract exactly the maximum power. We will see what we obtain. I have parameter sweep. I have to remove it because I don't need it. Yeah, this is 1000 now. The irradiance. Okay, let's see power, for example. Okay, you can see I will put also PV voltage. And I will put also what I need, the duty cycle that I am putting. Well, the duty cycle is already known. It is, I will put, for example, here. I will put the maximum power available in the, and you can see, because I am putting exactly that duty cycle, the duty cycle that gives the maximum power, you can see that the power of the PV is converging to the maximum power available in the circuit. Evidently, there is a small difference because of numerical errors, but you can see that it's a very, very close to 10 kilowatt, as we know already from the PV generators that you are using. Okay, let's say the importance of using the right duty cycle. Let us put, for example, 0.3. Okay? Okay. And you will see that the power now generated from the PV power, from the PV generator, is less than the maximum available power. You can see, right? It's less. There is a huge amount of power which is lost, and this is not desirable. If we use a larger value also of the duty cycle, we will have also less power generated. You can see that the power generated, even if I will use, for example, bigger value of the duty cycle, so I will have even an oscillatory system. So it is very important to have the right value of the duty cycle to provide or to extract the maximum power from the PV generator. Okay, so for this reason, an Mppt algorithm is used. So let us now use the Mppt algorithm. In this case, I will multiply this value by 0, it is disabled, and I will use the maximum power point tracking algorithm that I used before for the voltage source. Is this the same, which is implemented in the C code. And let's see what happened. I have a problem here. What is the problem? Just a moment. Node of a control power interface. What is, here. Just a moment, when I enable and disable, there is always some problems I have to solve. Okay, just a
Doctor,
moment.
just to make sure, when you have problems during the implementation of the circuits,
yes,
does the program give us notes where the problem is, or
so
we have to look
the problem? The program tells you that there is a problem, and as a message. For example, in this case, it is telling me error message, node of a control power interface floating. So,
and then we have to look at it.
It is a bad connection in my circuit I have to detect. Let's see, just a moment.
Okay.
Here it is okay, it is okay. It is okay here. Okay. Still giving the same message. I have this problem here also. Sometimes I have to close and okay. This one is okay. I will disable only the inverter side. Okay, this one is multiplied by 0. It is not operating, and the right duty cycle now is given by the Mppt algorithm. So I will simulate the system under these conditions. Let's see if I don't have any other error. It seems that we don't have any error. Simulation will be a little bit slow in this case, but I can make it faster. Just a moment. Okay. So we have now the PV generator, we have the boost converter, we have also the Mppt controller. We are simulating all these circuits. So you can see that I start simulating my whole system by simulating the different parts for make the task of simulation easy. Okay, and also for you to understand the importance of each part in the circuits. Okay, it is uploading that data. And let's see what happened. Okay, this is PV. I think it is not converging now to, yes.
I think so too.
It is not conversion to the maximum power. What is the reason? I will see again.
Not with the time.
Maybe the time, yeah, maybe the time. But I give it a large time. Maybe it is another problem. Let's see the duty cycle generated. The generated duty cycle is smaller than the one. Okay, but why? Maybe the parameters of the Okay, this one is okay. Let's give it, we recall from before that there are two parameters, the amplitude and the period. So these two parameters can make the Mppt algorithm to be fast or slow. So I have increased the amplitude. I hope it will be faster and converge to the maximum power more easily. Can you tell me please time? I'm not controlling.
Yes, it's 1:22 in our time.
We have only
which leave us for like more than 10 minutes. Yes, something
okay.
like that.
Okay, so maybe I will skip some slide. I will make the simulation of the complete system to see that the different tasks of this PV system are all satisfied.
Mm-hmm.
Okay, let's see now. Okay, it was.
I believe that you get the idea. Oh.
Yes, you can see that the system, after a large transient, it converges to the maximum power. The duty cycle also reached its desired value. The PV voltage reached its desired value, and everything is working as expected.
As it should
be. Yes, now we will use the full simulation of the system, because we don't have time to enter in the details of the inverter. Basically, we have here the inverter, which now will convert the DC voltage here, the DC link voltage, and it will convert it into AC. In fact, it is connected to the grid, which is an AC signal with the sinusoidal voltage. And the main task of this DC to AC inverter is to inject an AC current, sinusoidal current, but it must be in phase, synchronized with the voltage at the grid. So for that, we use what we call phase locked loop, and a PLL. We don't have time to enter into details, but this PLL, basically it gives a signal, sinusoidal signal, which is proportional to the grid voltage with amplitude equal to 1. This signal, sinusoidal signal, if it is multiplied by a reference, it will give the template for the current to be, for the grid current. So the grid current must track this template that we have generated. And for that, we use a controller, in this case, a PI controller, in order for the grid current to track the sinusoidal template and to be in phase with the voltage of the grid. The amplitude of the RMS value of the reference of the grid current is in turn provided by another controller that control or regulate the DC link voltage here. Okay, and the reference for this controller is the voltage that we want to have at the DC link. We have told before that this voltage must be 380 volts. So we will try to simulate this complete system and see the simulation corresponding to it. Let's see if everything is okay. I think we need, okay, this is okay. We need more time of simulation. I will put it, maybe I can show you the slide also, because simulation time is very, very large. So, okay, we have it already with the DC side, with the DC-DC boost converter and its control and Mppt algorithm. And now we will move to the DC-AC inverter, okay? So this is the DC-DC inverter. I have explained before how it works. The main task of this inverter is to inject grid current, but this grid current must be synchronized with the grid voltage, and this is called power factor correction. Simulations with Pcm, you can run some simulation, but I will present for you some simulation result that I have already prepared for you. Okay? So this is a simulation by considering the grid current as a constant. And I have provided it the value that gives the maximum power, that extract the maximum power from the PV source. In this case, the amplitude of the grid current is about 66 amperes. Okay, and you can see that effectively, the grid current tracked perfectly the reference given by us, which is a sinusoidal signal with amplitude equal to 66 amperes. You can see that they are synchronized, and both of them are in phase with the grid voltage. And this is very important. This is what we call power factor correction. Now, instead of giving the reference manually, I mean, I will not give you, I will not give this value, but I will make it to be provided by a controller. This controller controls the voltage at the DC link here. And by means of a PI controller, I will get the right value of the amplitude of this reference. When multiplied by the same sinusoidal signal, it generates a reference for the current. And this error between the grid current and the reference current is controlled again by another PI controller, whose output is introduced to the PWM, to the pulse width modulator, to control the switches of the inverter. Okay, so when we do that and we make a step change now, I make step change in the irradiance level from 0 to 0.8, I have 1000 watt per meter square. And at time instant 0.8, the irradiance is stepped down to 500. And again at 1.2, the irradiance step up again to 1000. So we can see this is the startup, and we can see that the power extracted from the PV generator reaches the maximum power in less than 1/2 second. When we apply a step change to the irradiance, the system again extract the maximum power from the PV, the maximum available power from the PV voltage. Recall that when the irradiance is lower, the maximum power is also lower. So here we are extracting less power than in this case. And again, when the irradiance increases again, we have the system also recover the extraction of the maximum power available. And basically we have the PV voltage is regulated to its the one corresponding to the maximum power. The duty cycle provided by the Mppt controller is the right value that guarantees the extraction of maximum power. And you can see also here in the grid side that the grid current is in phase with the grid voltage, and it is tracking perfectly independently on the value of the irradiance. It is tracking the reference current given by the controller. And finally, you can see here that the DC bus voltage is well regulated to its desired value, which was 380 volts. And you can see that all the tasks needed for the PV system are guaranteed. That's all. Thank you very much for your attention. I'm very happy if you have any question.
Thank you, Doctor, very much for this amazing introduction for this topic. And as Doctor mentioned, whether there are further questions, you can join us by your...
There are many chats, but I cannot,
yes, by chat or by voice.
Yes, there are some chats, but please, can you read and tell me if there is any?
Yes, no problem.
Okay.
Okay. Doctor, about the PV system,
yes,
you have mentioned before that it should be performed at maximum power.
Yes.
Why is that, actually?
Yeah, if you have a PV panel that can generate 10 kilowatt, the power is money. Why you will use it for generating only 2 kilowatt? Okay, much power you can, better.
And
in fact, this is what we pay to the electrical company. Power and energy. So much power, much energy, so much money.
طيب البراء تفضل البراء.
Assalamu alaikum.
وعليكم السلام ورحمة الله.
I want to ask you about is that okay if I use a buck converter instead of boost converter to find MPPT?
Yes, thank you very much for the question. Yes, you can. The only thing that you have to take into account that if you use a buck converter, the voltage at the input of the converter must be larger than at the output of the converter. Are you getting my point?
Yeah.
Okay, so in our case, for example, we are using a PV panel who is giving a voltage of about 248 volts. And the DC bus, the output of the converter was 380 volts. So I have to use a boost converter. But imagine you have a PV panel giving 600 volts. And the DC bus is 380 volts. Yes, in this case, you can use a buck converter. And you must use a buck converter. If you use a boost converter, it will not work. Okay?
Okay. Thank you.
You're welcome.
Okay, محمد مطرود تفضل. Okay.
I'm not here because maybe he has muted the microphone.
No. It's up to him. I have chosen to unmute himself manually.
Okay, but he's raising his hand, but I'm not hearing him.
I believe he's just asking about the certificate about today's meeting.
Okay.
Okay. Whether there are further questions about today's topic? I believe there were a question before, Doctor, about the power converter. The question was
the chat.
Is it going? Yes. Is it going to be 100% ideal? Because in real life, there is nothing 100% ideal.
No.
There are, of course, power loss.
He is right. I didn't want to make the presentation very difficult by introducing losses, and I wanted to be as much simple as I can, and the system as much ideal as possible. Evidently, in practice, there will be losses, and we will not have 100% efficiency.
Yes.
Yes.
Because in real life, there is nothing with no power loss. Doctor, earlier on the
hello.
Yes. Someone is talking.
Hello, Doctor.
Yes, Jamil. تفضل.
His bandwidth is very low.
Hello, thank you much, Doctor. And I want to ask about solar panel cooling. Does it have an impact on design calculation?
Yes. I didn't change the temperature in these simulations. I only changed the irradiance. But evidently, I didn't mention that, and thank you for asking. Evidently, the PV curve also depends on temperature. So in hot temperature, they have tendency to give less power. Evidently, by cooling them, we will improve the efficiency of the PV generators. Yes, you are right. If we cool the PV generators, we will improve the efficiency and we'll get more power.
Thank you.
Assalamu alaikum. Excuse me, Doctor.
Wa alaikum salam.
Doctor, what if we need to inject reactive power to the system from the PV module?
So you have to stop performing power factor correction. You have to see what is the difference, the angle difference between your your voltage and current, and you have to make the control in such a way that you have this phase difference in order to have reactive power.
So we need to introduce a control element, a new control element.
The same controller, but you have to use a reference signal for the grid current, which is not synchronized to the grid voltage. So we don't have to synchronize to the grid voltage. In this way, we will inject both active and reactive power.
Is that clear, Ahmed?
Yes, very clear. Thank you.
Doctor, I have a question earlier on the simulation. I have saw the section that was called shift locked loop, I believe.
Yes.
Yes.
PLL.
Was that just to make sure that the voltage and the current are in the same phase, or? Exactly.
What it do is to give you, I think it is here. It gives you the PLL. It gives you a sinusoidal signal with amplitude equal to 1, but which is synchronized to the grid voltage. Okay?
Okay.
And this is multiplied by the reference to give you the reference for the amplitude of the reference to give you the grid current reference. Okay? The PLL is only to get this sinusoidal signal which is in phase with the grid voltage.
Okay.
Okay.
Okay, that's clear. Thank you, Doctor. Susan, تفضلي. نعيد ترى المشاركة الصوتية وعبر الشات it's available يعني.
العفو دكتور، هل يتم منح شهادة
Yes, it's
السعودية
available.
الحبيبة الشقيقة.
في رابط عبر الشات أرفقت أكثر من مرة. You can fill your information.
نعم، تم تسجيل، أنا فعلت. Okay. نعم، أمليت الاستمارة. نعم، شكرا.
Okay, thank you.
شكرا جزيلا. شكرا.
زايد، تفضل.
دكتور أنا ما عندي رقم جامعي، فعادي كذا يعني ولا إيش؟
Yes, it's okay.
Okay, تمام، شكرا.
السلام عليكم دكتور.
وعليكم السلام ورحمة الله.
Doctor, advise me which best from the software for simulation, MATLAB or your...
It is not mine. Okay, I told it before, it is my favorite software for simulating power electronics converters. MATLAB and Simulink is a general purpose simulation software. It is not designed only for power converters, and it is not optimized for power electronic systems. But Pcm, this is the advantage. It is designed and optimized for power electronic systems. So it is my favorite in this kind of applications.
Power electronic system, yes, it is the name of software.
No, it is called Pcm. If you want, I can write in the chat the web page in order to install a demo version. Pcm Power, this one. And you can see a lot of videos in YouTube about how this software works. I wanted only to give you some, how can I go to chat? Chat, where is chat? Here, okay. I will put in the chat the website, okay? Maybe you can see it already.
Yes. Just a second.
This is the website, you can see Pcm. They have other software like DSIM. DSIM is much faster than Pcm. This is the last product of this company. And they say this is this is the world's fastest simulation for power electronics. This is what they say. Okay, and simulation speed is very important.
Sorry, Doctor.
Yes.
How can I benefit from data set? How can use, or when I find some data set?
Data set.
Yes. About solar energy, yes.
But I didn't get your point. What is exactly you need? Which data? About what? If
I find some data set, I can make simulation. Yes, Doctor?
But it depends on which kind of simulation we want to perform. This kind of simulation, for example, I'm presenting here, don't need any data set. But maybe you are you want to mention another thing. Yeah, I know that in order to simulate other aspects of PV systems, you need data, but not the one I am presenting here.
Do you know the location or sub website about data set?
You mean, for example, the availability of irradiance, temperature in the world, something like this?
Yes, yes, Doctor.
I know there are some websites. I will see, for example, I put here solar map. Yes. Yeah, for example, if this website can give you you can see red color means a lot of sun. You can see Saudi Arabia, a lot of sun. But green color means much less sun, okay? So there are websites that gives you online data about sun and availability of solar energy. This one, for example, you could see that I just put solar map and you will have some website. There are many. For example, this was solar. This one, for example, you can see. Okay.
Okay, and download, yes.
Yes, photovoltaic electricity potential. Yeah, you can search in Google some available data and you can download.
Okay, thank you, Doctor. Thank you so much.
You're welcome. You're welcome.
Okay. At the end of our meeting, we would like to thank Dr. Abdelali. It has been an honor, really, Doctor.
Thank you, you all also for attending. Thank you very much.
Thank you. And yes, we have to thank everyone that have joined us today. Inshallah, hopefully, Doctor, in the future, we'll see you again in other lectures.
Inshallah.
Inshallah. As I have mentioned before, it has been really a great honor to have you here today with us.
It's also
an
honor for me.
Inshallah, see you next time.
See you next time. Goodbye.
Inshallah. Goodbye. Assalamu alaikum.
Goodbye. Alaikum salam.